Today our objective is to compare two proportions using confidence intervals in hypothesis test. When we're comparing two proportions, comparisons between two percentages are more common and more interesting than questions about isolated percentages. We often want to know how two groups differ. For example, is a treatment better than a placebo, or is this year's AP exam results better than last year's? In order to compare the two percentages, we need a ruler. Remember from last semester, our standard deviations don't add, but we can add the variance. Remember, we find the variance at standard deviation squared, if you've forgotten. So there's a little, side note for you guys. And this only works if our two samples are independent of each other. So our standard deviations of the sample proportions, notice this p hat 1 is from our first sample, and this p hat sub 2 is from our second sample. The standard deviation of the difference then is here. Now this formula is provided on your formula packet. It is on page 2 under Roman numeral 3, statistical inference. So in our primary example today, we have a recent survey of 886 randomly selected teens aged 12 to 17 found that more than half of them had online profiles. Some researchers and privacy advocates are concerned about the possible access to personal information about teens in public places online. There appears to be differences between boys and girls in their online behavior. Among those aged 15 to 17, 57% of the 248 boys had posted profiles, compared to 70% of the 256 girls. What is the standard error of the difference in the two sample proportions? Well, the first thing we have to do is I would underline critical information. We know that we have 886 altogether. We also know 57% of 248 boys and 70% of 256 girls. We also have to make sure that our samples are independent of each other. So we need to ask ourselves, are boys and girls independent of each other? And we assume that they are because the boys and girls are randomly selected. So notice our standard error is approximately 0.0425. Remember, the 0.57 comes from the 248 boys. The probability of failure is 43% with a sample of 248. Whereas for the ladies, we had 70% of 256, which means 30% would be your failure. You would type this into your calculator in one huge step, and you should get about approximately 0.0425. Our assumptions and conditions are essentially the same exact thing as they were for confidence intervals and for one proportion z-test. So we're still going to use a randomization condition. Our samples must be random. Remember, if we are selecting our sample without replacement, our sample must be no more than 10% of the population. The independent groups assumption is something you just have to think about. You don't necessarily have to state, but remember the two groups we're comparing must be independent of each other. And then the sample size condition, meaning the large enough counts or success fail, they both have to be at least 10 for each of the groups individually. Back to our example, we're going to recall our online profile. And remember, we have 57% of the 248 boys have posted online profiles compared to 70% of the 256 girls. Can we use these results to make inferences about all 15 to 17-year-olds? So we're going to find our conditions. So as we can see from our conditions, we have both boys and girls are randomly selected. The 248 boys and 256 girls is less than 10% of all teens. And for a success fail, our boys, we have approximately 141, and for successes. And our failures, boys without online profiles, is about 107. For girls, 256 times 0.7 is approximately 179. And for the failures of girls who do not have online profiles is approximately 77. So because everything checked out, because all four of these are at least 10, we can use our inference methods. As soon as our conditions are met, the sampling distribution for the difference of two proportions as follows. Notice that your mean is the difference of the two proportions, and our standard deviation is what we just found. To do a two-proportion z interval, if we assume the conditions are met, the confidence interval for the difference of two proportions are as follows. Remember, in the formula sheet, you're always going to start with the statistic. So our statistic is the difference of our two proportions, plus or minus our critical value. Because we're talking about proportions, our critical value is z star, and then our standard deviation of the statistic. So back to our online profile example. It says, again, among randomly sampled teens, 15 to 17, 57% of 248 boys have posted online profiles compared to 70% of 256 girls. What does the confidence interval say about their online behavior? Okay, so we're just going to follow our steps. So for our state, we're going to say P sub B is the proportion of boys with online profiles. And for P sub G, we're going to say the true proportion of girls age 15 to 17 with online profiles. Our name of our inference procedure is a two-proportion z interval. Our conditions we did previously. For our do step, we're going to take our proportion for boys minus the proportion for girls. The 1.96 comes from a 95% confidence interval, and the 0.0425 is the standard error we found earlier. When we simplify, we do get negative 0.213 to negative 0.047 approximately. And we would say we are 95% confident that among teens aged 15 to 17, the proportion of boys who post online is between 4.7% to 21.3% less than the proportion of girls. This suggests girls are more likely to post online profiles. You could have done girls minus boys as well. You just have to adjust your conclusion. In our next example, we have a public broadcasting station plans to launch a special appeal for additional contributions from current members. They send the same request for donations to everyone, but it goes to one group by email and to the other group by regular mail. The station was successful in getting contributions from 26% of the members they emailed only. So that is critical. 15% of those who received a request by regular mail. A 90% confidence interval estimated the difference in donation rates to be 11% plus minus 7%. And number one, we're going to interpret the confidence interval. Remember, the confidence interval is my proportion and the differences plus minus the margin of error. So we're going to say we are 90% confident that if members are contacted by email, the donation rate will be between 4% and 18% greater than if they received regular mail. Okay, so we're talking about the difference in donation rates. And to get the lower end of our confidence interval, we'll take 11% minus 7% and the upper end 11% plus 7%. In number 2, it says, based on this confidence interval, what conclusion would we reach if we tested the hypotheses that there's no difference in the response rates to the two methods of fundraising? So for our number 2, because 0 is not included in our confidence interval, we reject the null. There's evidence to suggest more members will donate if contacted by email. Now let's talk about hypothesis testing. A typical hypothesis test for the difference in two proportions is that of no difference. So two acceptable responses on the AP exam, you can say your null is p sub 1 minus p sub 2 is equal to 0, or you can say they are equal to each other. Remember, we are hypothesizing no difference, so the standard deviation for each proportion would be the same if we say there's no difference. This allows us to pool our counts to get one overall proportion. And remember, we're saying pooling is okay because we assumed our proportions are equal. So a typical hypothesis test and the difference of two proportions, again, look, we have our null up here. And because we are hypothesizing no difference, the standard deviation for each of the proportions would be the same. So when we find our p hat, we're going to take our successes for the first sample plus the successes of the second sample over the total, sample 1 plus sample 2. And look, we also have our standard error. Okay, so you're going to take your p hat pooled, q hat pooled divided by the first sample number, and p hat pooled, q hat pooled divided by the second sample, and then square root. The conditions for the two proportions z-test are the same as for the two proportions z-interval. When the conditions are met, we use the following model to calculate the test statistic and the corresponding p-value. So notice the 0 is the mean, that's going to be your null, and your standard error. Last example. In an effort to reduce healthcare costs, General Motors sponsored a study to help employees stop smoking. In the study, half of the subjects, 439, were randomly assigned to receive $750 if they agreed to quit smoking for a year, while the other half of 439 were simply encouraged to use traditional methods to stop smoking. None of the 878 volunteers knew that there was a financial incentive when they first signed up. At the end of 1 year, 15% of those in the financial rewards group had quit smoking, while only 5% in the traditional group had quit smoking. Do these results give convincing evidence at the alpha of 0.01 that a financial incentive helps people stop smoking? And we're going to go through our 4 steps. For our state step, we're going to say P1 is the true proportion of employees who quit smoking when offered a financial incentive. Our P sub 2 is going to be the true proportion of employees who quit smoking with traditional methods. Our null hypothesis is going to be P1 minus P2 equals 0. And our alternative, because we want to see if the financial incentives increases the rate of smokers who quit, we're going to use P1 minus P2 is greater than 0. So for our plan step, we're going to use a two proportion z-test with an alpha of 0.01. Our first condition is the random condition, and it is stated in the problem that the volunteers were randomly placed into groups. 10%, 878 employees should be less than 10% of all GM employees. And our success fail, our number of successes for financial incentive is about 65.9 or 66. For failures, about 373.15 or 373. And for no financial incentive, our probability, our number of successful quitters is about 22 or 21.95. In failures, about 417. Now we're ready to talk about our do step. Two proportion z-test is unusual because, remember, we assume that the proportions are equal. We have to pool their proportion. So how we do that is we take our successes from both groups and add them together, and we're going to divide by the total from both groups. And it should give us a new combined p-hat of about 0.1102. Now, when we do our z-score, we're going to take our p1 minus p2. We always subtract the null, and then we use our new standard error. Because we had to pool our proportions, Our probability of success is the 0.1102, which matches over here. And 1 minus 0.001002 is 0.8998. And we're going to divide that by the first sample, 439, and then do the same thing for the second sample, 439. Now, you can type this all into your calculator in one step, but you have to be cautious of parentheses. The other thing you can do is you can run a two-proportion z-test, and it should give you approximately the same z-score. So our p-value, according to our chart, is approximately 0. If you run a two-proportion z-test in your calculator, it is also approximately 0. Remember, if it has a lot of zeros in front of a number, it's usually in scientific notation. All we have left to do is our conclude step. So for our conclude, skincare. Pretty sure it should say since. Whoopsies. Let me fix that. Since our p-value was low, meaning approximately 0 is less than our alpha 0.01, we reject the null. We have strong evidence to suggest employees like these are more likely to quit smoking, even given a financial incentive, than those with traditional methods. Hooray, we can do our practice now. The end.